Hi everyone, today we're going to study addition and subtraction of matrices. Addition and subtraction can only be done if the matrices being used are of the same dimensions. These operations are done with the corresponding elements of the matrices involved. Resulting matrix will have same dimension along with the given matrices. Example 1. Given matrix A equals 4, minus 3, 6, negative 8, 5, negative 9, respectively. Matrix B equals negative 5, 6, negative 2, 3, 7, negative 4, respectively. Evaluate A plus B. We note that both matrices are of size 2 by 3, meaning 2 rows by 3 columns. Thus, they have same dimension. So the A plus B, we need to add corresponding elements. So we will have like this. So this is 4 plus negative 5, negative 3 plus 6, 6 plus negative 2, negative 8 plus 3, 5 plus 7, negative 9 plus negative 4. When we simplify, we have now the elements negative 1, 3, 4, negative 5, 12, negative 13, respectively. We see here that the resulting matrix is of size 2 by 3 also. This is the final answer. Example 2. Given matrix A, 6, negative 7, negative 4, 5, negative 3, 2. Matrix B, negative 8, 3, 3, negative 1, 2, negative 8, respectively. Let us evaluate A minus B. We note that dimension of both matrices is 3 by 2, meaning 3 rows by 2 columns. For the A minus B, we're going to subtract corresponding elements. So we will have like this. And this is 6 minus negative 8, negative 7 minus 3, negative 4 minus 3, 5 minus negative 1, negative 3 minus 2, 2 minus negative 8. So the difference A minus B will have 14, negative 10, negative 7, 6, negative 5, 10. We know that the resulting matrix is of size 3 by 2 also. This is the final answer. Example 3. Given matrix A equals 2, negative 3, 0, 1, 2, negative 5, and matrix B with elements 3, 1, 2, negative 3, 2, 5. Evaluate. The first one is A plus B. The second is A minus B. Note that the dimension of both matrices is 2 by 3. Let's begin with A plus B. The rule says we add or subtract corresponding elements. In here, we're going to add the elements respectively. And this is the answer. This 5 means 2 plus 3. Then negative 3 plus 1 is negative 2. 0 plus 2 is 2. 1 plus negative 3 is negative 2. 2 plus 2 is 4. Negative 5 plus 5 is 0. This is the sum of two matrices. And then we go to A minus B. This time, we're going to subtract corresponding elements. And the answer is here. This negative 1 comes from 2 minus 3. Then, negative 3 minus 1 is negative 4. 0 minus 2 is negative 2. 1 minus negative 3 is positive 4. 2 minus 2 is 0. Negative 5 minus 5 is negative 10. This is the difference. Note that the resulting matrix is of size 2 by 3 also. There are notes to remember here. Note number 1, matrix addition is commutative. That is, the matrices A plus B is equal to B plus A. Second, matrix addition is associative. The group of matrices A plus B, then plus C, is equal to the matrix A plus the sum of matrices B plus C. Note number 3, matrix subtraction is not commutative, and that is A minus B is not equal to B minus A. Today, we're going to study scalar multiplication. Given a matrix capital A and K is a scalar. Scalar multiplication is the product of K and A. Thus, Ka. So this is K times A. It can be done on any matrix since it is simply applying the distributive property. Thus, multiply each element of the matrix by the number or the scalar before the matrix. Example 1, given matrix A equals negative 4, 3, 6, negative 2 respectively. Perform 5 times A. 5A here is equal to 5 times this matrix A. So we're going to multiply each element of the matrix by the number before the matrix. So we have like this. 5 times negative 4, negative 20. 5 times 3, 15. 5 times 6, 30. 5 times negative 2, negative 10. This is the final answer. Example 2. If matrix A equals negative 3, 2, 2, 1, 5, 0, and matrix B equals 0, negative 5 over 2, 1, 2, 3, negative 1 respectively. Then find 5A minus 2B. Let us evaluate 5A minus 2B. So we have 5 multiplied by the matrix equivalent to matrix A minus 2 times matrix B. So we multiply each element of the matrix by the number before that matrix. So the first matrix here becomes negative 15, 10, 10, 5, 25, 0 respectively. Then minus The second matrix becomes 0, -5, 2, 4, 6, -2. And from here, we're going to subtract corresponding elements. So we have now this matrix, -15 minus 0, -15. 10 minus -5 is positive 15. 10 minus 2 is 8. 5 minus 4 is 1. 25 minus 6, 19. 0 minus -2, positive 2. This is the final answer. Today, we're going to study equality of matrices. Two matrices, capital A and capital B, are equal. Written, capital A equals capital B. If they have the same size and their corresponding entries are equal. That is, A sub ij is equal to B sub ij for all I and j. Let's have example 1 given four matrices, capital A, capital B, capital C, capital D. We're going to compare this matrix A to the three other matrices. We have number 1, matrix A is equal to matrix C. Both matrices have same size, that is 2 by 3, and corresponding entries are same. Second, matrix A is not equal to B, since these matrices do not have equal corresponding entries. Number 3, matrix A is not equal to matrix D, since the matrix sizes are different. Matrix A is a 2 by 3 matrix and matrix D is a 3 by 2 matrix. Example 2, solve for x and y if the column matrix with first entry 2x plus 5. The second entry is y minus 3 is equal to the column matrix 11, 7 respectively. We say that corresponding entries of equal matrices are equal. So we can write like this. 2x plus 5 is equal to 11. Also, y minus 3 is equal to 7. Let us now solve for the x and y. Starting with the x. So we copy the equation 2x plus 5 equals 11. Let us isolate the variable x. This constant 5 we will transpose to the right. The sign is changed. So we have now 2x equals 11 minus 5. And we simplify the right side to be 6. We divide this equation by 2. So we get the value of x as 3. Let us now solve for y. We copy the second equation. Y minus 3 equals 7. Let us isolate the y. This negative 3 we transpose to the right. So we have now y equals 7 plus 3 and the right side becomes 10. This is the value of the y. Today, we're going to study multiplication of matrices. Multiplication can only be performed if the number of columns of the first matrix equals the number of rows of the second matrix. Then the process is carried out by doing row by column multiplication. Let matrix A equals the element A sub ij, and this is with subscript m by n, be an m by n matrix, and capital B equals matrix with element small b with subscript jk, and this is with another subscript n by p, be an n by p matrix. Then the product of the matrices A and B is the matrix capital C of order m by p. To illustrate, suppose we have here two matrices, matrix A with dimension m by n, matrix B with dimension n by p. Note here that the column of n is equal to the row of B. For the product AB, the size of this product will be m by p. The m comes from matrix A and the p comes from matrix B. Example, if matrix A equals 1, -3, 0, 2 respectively, and matrix B equals 1, 0, -2, -1, 2, 3 respectively, then find the product AB. First, let us note that matrix A is a 2 by 2 matrix, and matrix B is a 2 by 3 matrix. We can see that the column of A is equal to the row of B. Therefore, AB is defined. Then later, AB is a 2 by 3 matrix. The 2 here is the number of rows that comes from the row of A, and the 3 here is the number of columns that comes from the number of columns of matrix B. Then we will do row-column multiplication. It becomes like this. We're going to use the rows of A to be multiplied by the columns of B respectively. For the first element here, we will multiply the first row of A by the first column of B. For the element here, the row 1 of A multiplied by column 2 of B. Row 1 of A multiplied by column 3 of B. Row 2 of A multiplied by column 1 of B. Row 2 of A multiplied by column 2 of B. Row 2 of A times column 3 of B, respectively. Applying this, we will have the following numbers. For the first element, we will have 1 times 1 plus -3 times -1. Second element here will be 1 times 0 plus -3 times 2. Third element, 1 times -2 plus -3 times 3. Fourth element, 0 times 1 plus 2 times -1. Next, 0 times 0 plus 2 times 2. Then 0 times -2 plus 2 times 3. And from here, we will simplify the numbers. The first element becomes 4. The second element here is negative 6. The third element is negative 11. This element is now negative 2. The element becomes 4. And the last element here is positive 6. Note that the product AB is a 2 by 3 matrix. This is the final answer. Example 2. Given matrix A with elements 6, negative 2, 3, negative 4, 2, 5, and matrix B with elements 2, negative 3, 4, negative 5, 1, negative 6. Find the product AB. First, we identify the size of matrix A, that is 2 rows by 3 columns, so 2 by 3. What about the size of matrix B? That is 3 rows by 2 columns. So we write here 3 by 2. As a rule for the product, the number of columns for the first matrix must be equal to the number of rows for the second matrix. If this is so, the product AB is defined, and AB should have the size 2 by 2. Now let's start writing the elements for the product AB. Let's begin with first row, first column element. So we multiply corresponding elements. So we have 6 times 2 plus negative 2 times 4 plus 3 times 1. Next, second row, first column. So we have negative 4 by 2 plus 2 times 4 plus 5 times 1. Next element, first row, second column. So it becomes 6 times negative 3 plus negative 2 times negative 5 plus 3 times negative 6. Then, second row, second column. We have negative 4 times negative 3 plus 2 times negative 5 plus 5 times negative 6. Then we simplify the product. So we have 12 plus negative 8 plus 3. Down here will be negative 8 plus 8 plus 5. Next is negative 18 plus 10 plus negative 18. Then positive 12 plus negative 10 plus negative 30. Now we get the total for each of the elements. So we have here 12 plus negative 8 plus 3 is 7. Negative 8 plus 8 plus 5 is 5. Negative 18 plus 10 plus negative 18, that is negative 26. 12 plus negative 10 plus negative 30, total is negative 28. So we see here, as expected, the size of this product AB is 2 by 2. This is the answer. Example 3. Given matrix A with elements 2, 4, 1, negative 3. Matrix B 1, negative 1, 5, 0, 2, 6. Find product AB. We identify the size of matrix A to be 2 by 2. The size of matrix B is 2 by 3. For the product AB, the first matrix is A. So the number of columns is 2. For matrix B as the second matrix, the number of rows is 2. So they are equal. That means for the product AB, we expect the size to be 2 by 3. So we write it here. Now let's start to write the elements for the product AB. Let's begin with first row, first column element. So 2 times 1 plus 4 times 0. Next is first row, second column. So we have 2 times negative 1 plus 4 times 2. Then first row, third column. 2 times 5 plus 4 times 6. Next is second row, first column. So we have 1 times 1 plus negative 3 times 0. Next element, second row, second column. 1 times negative 1 plus negative 3 times 2. Then, second row, third column. 1 times 5 plus negative 3 times 6. Then we simplify the products respectively. We have 2 plus 0, negative 2 plus 8, 10 plus 24, 1 plus 0, negative 1 plus negative 6, 5 plus negative 18. Then we combine the sum. 2 plus 0 is 2. Negative 2 plus 8 is 6. 10 plus 24 is 34. 1 plus 0 is 1. Negative 1 plus negative 6 is negative 7. 5 plus negative 18 is negative 13. So we note again that the size of the product AB is 2 by 3. This is the answer. Let capital A, capital B, and capital C be matrices whose sizes are multiplicatively compatible, and K is a scalar. First property, the product AB is not equal to the product BA. We say that matrix multiplication is not commutative. Second property, the product of AB times matrix C is equal to matrix A times the product of BC. Now, matrix multiplication is associative. Third property, A times the sum matrices B plus C is equal to the product AB plus the product AC. Property number 4, sum A plus B multiplied by matrix C is equal to product AC plus product BC. 5. The scalar K multiplied by the product AB is equal to the product KA multiplied by B. And this also equal to the matrix A times the product KB. These are the properties of multiplication of matrices. Hi everyone. Today we're going to study special types of matrix. The first type is zero matrix, or we call it null matrix. A matrix with all elements that are zeros is called a zero matrix, denoted by capital O. Examples, we have two here. The first example is 0, 0, and this is a zero matrix of order 1 by 2. Second example, 0, 0, 0, 0. This is another zero matrix of order 2 by 2. A zero matrix represents the additive identity matrix of all matrices under the addition operation. If capital A is an M by N matrix and capital O is an M by N zero matrix, then A plus O is equal to O plus A equals A. Second type is column matrix. Sometimes this is also called column vector. A matrix is said to be a column matrix if it has only one column. Examples, the first one is with elements 4, 3. This is a column matrix of order 2 by 1. Next example with elements 1, 0, 6 respectively. This is a column matrix of order 3 by 1. Third type is row matrix or row vector. A matrix is said to be a row matrix if it has only one row. Examples, the first matrix with elements 1, 6 is a row matrix of order 1 by 2. Second example with elements -1, 2, 8. This is a row matrix of order 1 by 3. Fourth type is square matrix. A matrix in which the number of rows is equal to the number of columns is said to be a square matrix. Thus, an M by N matrix is said to be a square matrix if M equals N and is known as a square matrix of order N. Examples, the first one is a matrix with element 6. This is a square matrix of order 1. Second example with elements 1, -2, 3, -5 respectively. This is a square matrix of order 2. Third example, a matrix with elements 1, 7, 8, 4, -2, 6, 0, 9, 4 respectively. This is a square matrix of order 3. The elements A sub 11, A sub 22, A sub 33 up to A sub NN are said to constitute the main diagonal of the matrix. In our first example, with only one element, the main diagonal is itself. So the element in the main diagonal is 6. In the second example, the main diagonal elements are 1 and -5. In the third example, the elements in the main diagonal are 1, -2, 4, respectively. Fifth type is the diagonal matrix. A square matrix A is said to be a diagonal matrix if all its non-diagonal elements are 0. That is, A sub ij is equal to 0 when I is not equal to j. Example, we have 1, 0, 0, 0, negative 2, 0, 0, 0, 4. We can see that the elements in the main diagonal are 1, negative 2, 4, and the remaining elements are all 0. This is a diagonal matrix of order 3. Sixth type is the scalar matrix. A diagonal matrix is said to be a scalar matrix if its diagonal elements are equal. Example, this is a square matrix. This is also a diagonal matrix. The elements in the main diagonal are equal and all 8. The remaining numbers or elements of the matrix are all zeros. So this is a scalar matrix of order 3. Seventh type is the identity matrix or unit matrix. A square matrix in which every diagonal elements are 1 and non-diagonal elements are zeros is called an identity matrix. An identity matrix of order n is denoted by capital I sub n. We have here three examples. I sub 1 is equal to the matrix with only one element, which is 1. And this is of order 1. Second example, I sub 2 is equal to the square matrix 1, 0, 0, 1 respectively. The elements in the main diagonals are all 1. The remaining elements are zeros. And this is of order 2. Third example, I sub 3. This is a matrix with elements 1, 0, 0, 0, 1, 0, 0, 0, 1. The elements in the main diagonal are all 1s. The remaining elements are zeros. And this is of order 3. If A is a square matrix of order n and I sub n is identity matrix of order n, then the product A times I sub n is equal to I sub n times A is equal to A. Eighth type is the upper triangular matrix. A square matrix in which all elements below the main diagonal are zeros is called upper triangular matrix. We have here one example. The elements in the main diagonal are 2, 8, 7 respectively. We can see here that the elements below the main diagonal are all zeros. So this is an example of an upper triangular matrix of order 3. Ninth type of special matrix is the lower triangular matrix. A square matrix in which all elements above the main diagonal are zeros is called lower triangular matrix. Example, we have here 2, 0, 0, 3, 8, 0, 4, 5, 7 respectively in this matrix. In the main diagonal, the elements are 2, 8, 7. We can see that all the elements above the main diagonal are all zeros. This is an example of a lower triangular matrix of order 3. Today, we're going to study transpose of a matrix. If capital A be an M by N matrix, then the matrix obtained by interchanging the rows and columns of capital A is called the transpose of A. Transpose of the matrix A is denoted by A apostrophe or A with exponent capital T or A with exponent small t. In other words, if capital A is the matrix M by N, then A transpose is equal to the matrix N by M. Example, if matrix A has these elements 3, 1, -5, 12, 7, 6 respectively, we can see that this is a 2 by 3 matrix. Then the A transpose is equal to this matrix. So you see here, the first row of matrix A is equal to the first column of A transpose. Also, the second row of matrix A becomes the second column of the A transpose. We observe also that the A transpose now is 3 by 2 matrix. Let's go to symmetric matrix. A square matrix A is said to be symmetric if A transpose is equal to A. That is, the matrix with element A sub ij is equal to the matrix with element A sub ji for all possible values of I and j. Example, matrix A with elements 3, 5, 5, -7. This is a 2 by 2 matrix. This is a symmetric matrix because the A transpose is equal to this matrix. We can observe that the first row here becomes the first column of A transpose. Also, the second row of the matrix A becomes the second column of A transpose. We note that this is also a 2 by 2 matrix. Comparing the two, this A transpose is also equal to that matrix A. Therefore, this matrix A is symmetric. Let's go now to skew symmetric matrix. A square matrix A is said to be skew symmetric if A transpose is equal to the negative of the matrix A. That is, the element A sub ji is equal to negative A sub ij for all possible values of I and j. Note that all the diagonal elements of a skew symmetric matrix are 0. Example, matrix A with elements 0, 5, -5, 0. We can see here that this is a 2 by 2 matrix. Also, the elements in the main diagonal are all 0. This is a skew symmetric matrix. because the A transpose is equal to this matrix. The first row of matrix A is the first column of the A transpose. The second row of matrix A is equal to the second column of A transpose. We can see that the A transpose is also a 2 by 2 matrix. If we compare this A transpose with the matrix A, this A transpose is equal to the negative of the matrix A. Therefore, this matrix A is skew symmetric. Let us study orthogonal matrix. A square matrix is orthogonal if A times A transpose equals I, or the identity matrix. Example, if matrix A equals with the elements sin x, cosine x, negative cosine x, sin x respectively, then verify that A times A transpose is equal to capital I. For our solution, first we will write the A transpose. The elements now are sin x, negative cosine x, cosine x, sin x respectively. Then we're going to multiply A by A transpose. So we will write our matrix blank here. We will do and start the row column multiplication. So the first row multiplied by the first column. So we have here sin x times sin x plus the cosine x times cosine x. For the element here, we have sin x times negative cosine x plus cosine x times sin x. For the element below, we have now this negative cosine x times sin x plus sin x times cosine x. Then the last will be negative cosine x times negative cosine x plus sin x times sin x. From here we can simplify the sin x times sin x into sin square x. For this we can write cosine square x. We have here also the negative cosine x times negative cosine x. We write here cosine square x. And for this, we have the sine square x. For sine square x plus cosine square x, we can apply the rule of trigonometry identities. Also, we can write the same identity idea for this expression. In here, we are going to use the simple algebra. The sin x times negative cosine x will be negative sin x cosine x plus this is sin x cosine x. Later, if we add, this will be 0. Down here will be negative cosine x times sin x is negative sin x cosine x plus this sin x times cosine x will be 0. The product A times A transpose will be equal to, this is equal to 1, this would be 0, this is also 0, and this is 1. We can see here that the resulting matrix is equal to the identity matrix of order 2. Therefore, the matrix A here is orthogonal. Here are the properties of transpose of matrix. For any matrices A and B of suitable orders, and K is a scalar. First property, the transpose of A transpose is equal to A. Second, the transpose of the sum A plus B is equal to A transpose plus B transpose. Third, the transpose of the product A times B is equal to B transpose times A transpose. Fourth, the transpose of the product K times A is equal to K times A transpose. Fifth, A plus A transpose is always symmetric. The last, A minus A transpose is skew symmetric. I hope you learned something from this video. See you again next time.